Hello everyone, this video is about common collector amplifier. And common collector amplifier means the amplifier has its collector terminal ground. So I will write down the important point here. Collector is ground. It can be AC ground. And the most popular circuit topology for common collector amplifiers is like this. We have a source voltage and there isn't any resistor between the voltage source and the collector. Instead, the collector is connected straight to the voltage source. So down here, we are going to collect the voltage right at the emitter. Maybe we need to improve the handwriting. This one VCC, and then VO, and then we have the input here. Now we are going to analyze the circuit. The first step is to replace this transistor with its small signal equivalence. There are many models you can. There are many small signal models you can use. From my perspective, I think the T model is the best one. So we can start with the T model with B terminal here, and then we have a current source here. And this current source is GM and then VBE. And then the output it is connected to 1/GM, and then the RE is connected here, and V out. And we are going to ground this terminal. And we don't know the current, the output, the collector current. So the first thing that we want to know is the transfer characteristic. By looking at the circuits here, we have the current going into here, IB, and the current going down here, IE. Yeah. And VO is equal to IE times RE, and in is equal to IE times 1/GM plus RE. So this is the way to make our life easier. We don't need to struggle with all this current source or whatever. So based on the equation given here, we can say the voltage gain is equals to V out divided by V in, which is IE, RE, and then 1 over GM plus RE. So eventually, if you do it carefully, you will notice the final expression is more or less like this. So if RE is large, if RE is large enough, to produce a condition maybe you just say GMRE is greater than 1. In this case, VA, the AV, the voltage gain is more or less 1, depending on the value of the emitter resistor here. Now, there isn't anything interesting here. Input is equal to output. So there is another name for this amplifier. It is also called voltage follower. Also called voltage follower. But then there must be some justification. If it is just a voltage follower, then there is no use at all. But hang on a minute, I'm going to show you. The beauty of this circuit is the input resistance is very high. Now, starting from here, I'm going to work out the input resistance. So, input resistance based on what we have got here. The input resistance is the sum of these two resistance. Now, input resistance by definition is the input voltage divided by IB. And we can say that you can say IE and then 1 plus beta. Yeah. We can use this way to find the equation. And now VE divided by IE. The voltage here divided by IE. IE is this current. So isn't it going to be 1 over GM plus RE? Yes, the answer is yes. So 1 plus beta, and then 1 over GM plus RE, depending on the on your requirement. And normally, in these circuits, we need to simplify it further in order to visualize the actual value to get the physical feeling. Uh, so you have GM here, and you multiply this by here. Let me see. Input impedance beta times RE. So now, based on this expression, 1 over GM is a small value, and we can say that RE is much bigger than 1 over GM. It's not. 1 over GM is a large figure. Okay, let's continue. 1 plus beta, and then 1 plus GM RE. Yeah? And previously, we have already said that this expression is going to be very much bigger than 1. So we can say 1 beta, and then GM RE divided by GM. So finally, what we end up with is 1 over beta and then RE. So this is just an approximated expression. The larger the beta, the larger of the forward current gain, the higher the input impedance that you will get. And also the choice of the tail resistance here is also important. We should choose a large value in order to get the maximize the input impedance. Now, the input resistance is known, and the gain is almost 1. The input impedance is this value. The beauty of this circuit is it has a very large input impedance. But how about the output impedance? Output impedance, and according to here, output impedance is VR and then divided by RE, and let's say, let me say, output impedance here should be equal to, let me just erase this one. Based on my analysis, I see output impedance. Now, the first thing that we need is to short these signals to the ground. So essentially, what we are going to do is we are now evaluating the output impedance. The very first thing that you need to do is to short this to ground, and then we found the resistance, the output resistance, And this is the way how we found the output resistance in testing and Norton analysis. So based on the information here, the resistance is going to be RE in parallel with 1 over GM. And you can further simplify the circuit. RE and then over GM and then 1 RE plus 1 over GM. So we can further simplify the circuit by multiplying the top and bottom with GM. Hence, what we are going to get is this one here. And previously, we have already made an assumption. We want the value of the emitter resistance to be as large as possible. So large to an extent that GM times RE is much greater than 1. So in this case, we can approximate the circuits with. So in other words, by simplifying this expression, we know the output resistance is 1 over GM. So the output resistance is quite low. It depends on this value. Depends on the IC. We want the output resistance to be low. Then we want to have a large collector current in the biasing. So we want to have large biasing collector current. So now everything is resolved now. So the characteristic of this voltage follower is it has high input impedance and low output impedance. So we can work out we can write down the following. Unity voltage gain and high input impedance. And low output impedance. Maybe we should use resistance. This is the better term. And we change it to resistance. And then we change it to resistance. So in other words, if you have a P amplifier and the P amplifier is running out of output impedance, so what you can do is to use this collector circuit and then you add a driver here. And you just tap the output in here. So this is how we use the P amplifier. It could be a low noise amplifier, and then we just add one more stage here, and then the output will be powerful enough to drive off any low resistance load. Okay, if you have any question, please leave your questions to the comments box. And if we have time, we will try to tackle your questions. Thank you very much and have a nice day.